Welcome to the online lecture that includes electromagnetic radiation and atoms. In this lecture, we'll be taking a further look into atomic structure and how it relates to bonding and chemical reactions and the reactivity of different elements. To start off this lecture, we're going to talk about blimps. And you may or may not have seen a Goodyear blimp or a similar type of blimp flying around up in the sky at a sports event or something like that. But they are definitely unique modes of transportation. Unlike airplanes, they don't need to be moving fast. Airplanes and helicopters need to be moving fast through the air or through the sky so that they take advantage of Bernoulli's principle in order to stay in flight. However, blimps can go very slow. All right, and so they're actually used a lot for, camera, videotaping, and all that stuff because they can move slow. They don't have to be moving super fast to stay up in the sky to give, nice wide shots of aerial things. So how do blimps, okay, just like balloons, float? Well, it's because blimps these days are filled with helium, which is less dense than air. So if something is less dense than air, then it's going to float up in the sky. But why helium? Why do we use helium in blimps? Well, because, back in the day, in the early 1900s, they used to use hydrogen. Okay, except you can see down here, tragedy strikes when you use hydrogen in a blimp because it is very reactive and very flammable. In fact, this is a picture of the Hindenburg, the infamous German blimp that was filled with hydrogen that basically exploded in air. So, in order to avoid that situation, we use helium because helium is inert. It's not reactive and it won't be flammable. So, our question then, kind of for this unit, is what makes helium inert but hydrogen highly reactive? In order to answer this question, we have to take a look at the structure of the atom. All right, so we've got two basic modern models of atomic structure and theories about how the elements or the atoms are structured and therefore how elements behave. One is called the Bohr model, and the other is the quantum mechanical model. The Bohr model was developed by this guy right here, Niels Bohr, who came up with this type of model of the atom and its electrons and how they're arranged. And the other guy, Schrödinger, came up with the quantum mechanical model. Or at least he's the guy who coined it. There's a bunch of scientists that were kind of working on the same ideas, including Albert Einstein. But he was the guy who got credit for the quantum mechanical model. And so we're going to take a look at both. And both basically are models of electron organization. And so we're going to see how the electron is basically the parts of the atom that's going to either make the atom inert like helium or very reactive like hydrogen. All right, so before we talk about electrons, we have to talk about light, okay? Because in Niels Bohr and Schrödinger's experiments, they were basically using or observing light, okay, and making their observations and hypotheses and theories from that. And so they used the interaction of light with atoms to help build and shape their models. So we need to learn a little bit about light. So we know that light is not matter. It has no mass. Remember, matter has to have mass and volume. And so light has no mass, therefore it does not matter. In fact, light is a form of what we call electromagnetic radiation, or basically just energy. Light is energy that travels through space at 3.8 times 10 to the 8 power. Okay, remember my little application doesn't do well with exponents. So 3.0 times 10 to the 8th power meters per second. Okay, that's super quick because remember a meter stick, and now do 300 million of those in 1 second. Okay, so that's super quick. All right, so light is a form of energy, and light travels as waves that carry this energy. And so we can see, down here in the pictures. All right, first we have over here on the right, we've got a prism, okay, because we can split white light into varying colors through a prism, and we'll talk about what makes up those colors and so on and so forth. But that is one property of at least visible light. And then on the left, we have what's called the electromagnetic spectrum. It includes all electromagnetic radiation, not just visible light. So we're going to take a look and talk about the characteristics of electromagnetic radiation, the electromagnetic spectrum, and light. All right, so we said that light moves in waves. Okay, and so waves are characterized basically by two properties, wavelength and frequency. Okay, and wavelength is the distance between two adjacent wave crests. And so if you take a look at this picture down here, this is a picture of a wave, and the crests are the peaks, okay, and the bottom we call troughs. And so a wavelength is the distance between one peak to another, is a wavelength. Okay, so for visible light, different wavelengths are going to mean different colors. All right, and we see for other parts of the electromagnetic spectrum, the ones that have higher energy are going to have shorter wavelengths. The ones that have low energy will have longer wavelengths. I also said that waves are also characterized by frequency, and that basically is the number of cycles that pass through a stationary point in 1 second. So basically, if you were standing looking straight ahead and you were counting how many waves, crossed your path in 1 second, that would be its frequency. Okay. Now, frequency and wavelength are inversely related. All right. That means if you have a short wavelength, okay, you're going to have a large number for frequency. You're going to have lots of waves that can pass by in a second. If you have a really long wavelength, you're going to have slow frequency. Okay, so because it's going to take longer for those waves to pass by. So wavelength and frequency are inversely related. All right, so it would make it a lot easier if light just behaved like waves. However, through different experiments that chemistry and physics pioneers developed and performed, they actually found that wave behaves not just like waves, but also like particles. And so, a little particle of light is what we call a photon. You may have heard that before. It's a single packet of light energy. All right, so the reason why waves behave both as in, light behaves both as in waves and as particles is one of the simple experiments that they did was they shined a light and focused that light through, and I've got a picture down here, focused that light through little slits in cardboard. Okay, waves, when they come to kind of a break, I guess, they're going to kind of fan out, okay, as they go past that little slit there. All right, and we know that occurs. You can see that if you put barriers up, in basically, like if you think of a bay, all right, or a harbor, and they've got jetties, all right, and so the waves are going through, and then as the waves get out into the ocean, they're going to spread out and propagate. That's a property of waves. So we see that happen, but we also see as light goes through these slits, we get light and dark inner, fringes, basically, little streams or particles of light and dark shadows. All right, and that really doesn't happen with waves. That only happens if light acts as particles. So basically, light behaves as a duality, both as waves and as particles. So let's talk about the particle portion of waves, or sorry, particle portion of light. So that is the photon, and it's a single packet of light energy, and the amount of energy depends on the wavelength of light. So they're kind of related. The shorter the wavelength, the greater the energy. Okay, so if you see here, wavelengths over here on the gamma end, all right, are super short. That means gamma rays, gamma energy is the greatest. Over here on the left, you have radio waves, which are very long or big in wavelength, and so they carry less energy with them. All right, so let's take a look at the electromagnetic radiation spectrum. All right, so we have a wide range of wavelengths. Okay, basically from, and of course, my fun little app here is no good. So basically from 10 to the negative 16th power meters. Okay, so gamma rays are super, super, super tiny in wavelength. Okay, to 10 all the way to 10 to the 6th meters for radio waves. Okay, so 10 to the 6th is a million. All right, and 10 to the negative 16th is like, I don't know, way, really, really, really tiny. All right, so this is what we call the electromagnetic spectrum, going from super, super tiny wavelengths to really, really big wavelengths of energy. So let's start with the super tiny wavelengths. Gamma rays, okay, are over here on the electromagnetic radiation. We can see that they're super short wavelengths. They have the shortest wavelengths. Gamma rays are produced by the sun and stars and unstable atomic nuclei. Okay, so radioactive atoms emit gamma rays. Okay, so when they fall apart, they do alpha decay or beta decay, they are going to be releasing gamma rays. Gamma rays are, like we said, very short. If they have short wavelengths, they're going to have high energy. Okay, so short wavelengths equals lots and lots of energy. In fact, so much energy that it damages biological membranes. Okay, so that's why gamma rays and radioactive radiation is so dangerous, because it can cause cancer and illness and cells to die and all kinds of bad stuff. So we want to definitely stay away from gamma rays. The next on the electromagnetic spectrum is the X-rays. Okay, so they are they are longer in wavelength and have a lower energy than gamma rays. Okay, X-rays you probably know that are used for medical imaging, but just like gamma rays, even though they have a longer wavelength than gamma rays, they still have super high energy. Okay, compared to the other electromagnetic radiation. So they still have super high energy that can damage biological molecules. So that's why you don't want to have too many X-rays done on your body, because it can damage cells and cause cancer. Next up, okay, the next longest is ultraviolet light. So again, not as energetic as gamma rays or X-rays, because it has longer wavelengths. But again, still short enough, wavelengths and high enough energy to cause biological damage in biological molecules. So we have to be careful with the sun. The sun is going to produce UV rays, and that's what sunscreen basically is designed to protect us from, is the UV light, because it can damage our cells and cause skin cancer. All right in the middle of the electromagnetic spectrum is what we call visible light. And visible light is longer wavelengths and less energy than the previous ones, than UV, X-ray, and gamma rays. And this is the type of electromagnetic radiation that our eyes detect and help us to see. So this is, all the different colors, everything that we see is because the electromagnetic radiation is picked up by sensors in, sensor cells in our eyes, and it uses it to basically make images that we can see the world around us. So visible light does not cause damage to biological molecules, which is good. Otherwise, I'm not sure how long life would be, since light is, all around us, and our eyes use it and whatnot. So we'll talk more about visible light in a few minutes. Let's take a look at infrared. Infrared is longer wavelengths than visible light. Therefore, it carries less energy than visible light. Basically, if you think about every warm object emitting light, that is infrared. Okay, infrared is emitted by all warm objects. In fact, you may have seen infrared pictures or infrared cameras where the red part of the picture is something that's really warm, and it goes to orange and yellow, and blue is kind of the coldest. So that's infrared light. It's taken advantage of in night vision goggles. Basically picks up infrared radiation and translates it into images that we can see. So infrared light is less energy, and so it's not going to damage any biological cells or anything. All right, the last two that we're going to talk about are microwaves and radio waves. So microwaves are even longer than infrared. So again, they have lower energy. Microwaves are used in radar signaling and also in what we call microwave ovens. All right. So microwaves, yes, they have longer wavelengths, lower energy, but they still have enough energy to heat up water. Okay, so anything that has water molecules in it will be able to be heated up by microwave ovens. So that's basically how they work. Microwave ovens emit microwaves which carry energy that will heat up water, molecules that have water in it, which most food particles and stuff are, but they're not going to really heat up wooden objects or plates and stuff like that as easily. Obviously, if you keep the plate in there for a really long time, the heat from the food warms up the plate, but it's not actually the microwave oven that's warming up the plate. It's kind of weird to think about. In any case, so the myth basically, so if you think about this, microwaves have long wavelength, low energy, lower energy than infrared and visible light. So are they going to be hazardous to your health? No. All right, so that myth that microwave ovens cause cancer or whatnot is just that. It's a myth because the radiation coming from it is so low in energy it's not going to do any harm. Same with radio waves. Radio waves are the longest wavelengths and thus have the lowest energy. All right, we've been using radio waves for many years to transmit signals for communication devices. So started out with AM/FM radios that use radio waves to send signals. Ham radios, walkie-talkies, cell phones, now TV, all of those communication devices send information along radio waves that have long wavelengths and low energy. So it is highly unlikely, because it is the longest wavelength and the lowest energy, that it's going to do any damage to our bodies. And so we've kind of seen that because radios and such have been around for hundreds of years, and there hasn't been anything linked, any cause of death linked to radio waves. All right, so now that you know what you know about the electromagnetic spectrum, you can do this little exercise by putting the three types of electromagnetic radiation visible light, X-rays, and microwaves in order of increasing wavelength, frequency, and energy per photon. And so what that means is you're going to put visible light, X-rays, and microwaves from the least to the greatest. So least wavelength to the greatest wavelength, then do that for least frequency to the greatest frequency, and also least energy to the most energy. So I'll let you guys do that on your own. You can pause this and take a few moments to do that. We're going to move on now to talking about atoms and what light has to do with atoms and atomic structure. So when atoms absorb energy, and they're going to either absorb energy in the form of light, heat, or electricity, they often emit energy as light. Okay, and so we're actually going to see this, and if you remember from general chemistry, hopefully your teacher did those flame test labs where you put different substances in flame to heat it up, to add energy to those atoms, and the flame turned different color because those atoms in the substances were absorbing energy and releasing it as light. So absorption and emission spectrum of light by atoms is due to the interaction of light with electrons. So when you are doing flame tests, which you will actually do flame tests again this year, you're basically playing or messing with the electrons in the atoms. All right, so atoms of each element emit light of unique colors. And so here is the emission of hydrogen. Here is mercury. All right, and this one here is neon, actually. Okay, so there you go. This is basically hydrogen atoms, neon atoms, and mercury atoms that are absorbing energy from electricity, and as they absorb that energy and release it, they light up in different colors. All right, so Niels Bohr, one of those guys who came up with the first theory of atomic structure, looked at the emitted light from hydrogen, helium, neon, and other atoms through prisms, basically. And what he saw was that atoms of different elements excited with energy emit only particles at particular wavelengths. Okay, so if we look at white light, just visible white light through a prism, we see a spectrum. Okay, red, yellow, green, blue, and purple, kind of all blended together. Okay, there's no discrete lines, it's just all one kind of blended rainbow. That's visible light. However, when he looked through a prism at the light emitted by just hydrogen, okay, or neon, or in this case iron, okay, he saw different distinct bands of light, of colors. Okay, so it wasn't this, blending of all the different colors. It was distinct colors in distinct little bands. And so he was trying to figure out why is it distinct little bands, and why is it different for each different kind of element. Okay, so that's kind of basically the question he was trying to answer. And in trying to answer this question, he came up with a theory that it's got to be the electrons in an atom. Okay, the electrons traveling around the nucleus. That seemed to be the only part of the atom that would make sense to be, basically being energized or storing up energy and being able to release energy in the form of different light bands. And so what he hypothesized was that electrons travel around the nucleus in basically circular orbits, just like the planets travel around the sun in a very distinct circular orbit. In fact, he thought that electrons were in specific fixed distances from the nucleus. All right, and there were obviously different levels or different circular orbits. We can see here in this picture That the first one is closest to the nucleus, and there's one that's a little further away, and the one that's further away from that. Okay, and then, but as you get further from the nucleus, these orbits, okay, get closer to each other. And so he also hypothesized that the energy of each orbit is quantized, or basically you can measure it. And he gave quantum numbers, okay, 1, 2, 3, 4, if he has another ring, 5, 6, 7, 8. Okay, so he gave these quantized numbers to these orbits that he theorized were around the nucleus. Okay, and so he said that there's fixed orbits, each orbit has fixed energies, and each orbit is a fixed distance from the nucleus. And it's impossible for an electron to be between an orbit. So electrons have to stay in the orbits, okay? They cannot be between orbits. Okay, so you won't find electrons out here in the white spaces. Right? That is not possible in his thing. So those are not possible locations for electrons. They're very specific. All right, so his theory works, okay, because it kind of explains basically what he saw in his experiments. When he put energy into an atom, okay, when he electrified it, basically, electrons, he theorized, are going to be jumping from lower energy orbits to higher energy orbits. Okay, so electrons will be jumping from one orbit to another. Okay, remember, the further away you are from the nucleus, the higher the energy. The closer you are to the nucleus, the lower the energy. Okay, so when energy is put into an atom, those electrons jump into higher energy orbits. And eventually, okay, they're going to fall back down into, their lower energy, okay, their original energy states. And when they do that, okay, when they fall back down, that energy has to go somewhere, because remember, energy cannot be created or destroyed, just like matter. So that energy is released as light. And specific wavelengths of light. All right, and so he could actually kind of figure out the different colors that he sees correspond to different wavelengths of light that is being emitted as electrons jump back and forth between certain orbits. Okay, so a hydrogen atom would only, basically only has one or two different wavelengths, because remember, hydrogen only has one electron that's going to be jumping around. Okay, neon has more electrons than hydrogen, so we're going to have more little lines, and they're going to have specific wavelengths due to the energy that it absorbs and releases as those electrons jump from one energy orbit to another. Okay, and so iron has more electrons than neon, and so we're going to have more and more different bands of lights as we get more and more complicated orbits. Okay, so that basically is how he came up with his Bohr model of the atom, in which electrons have fixed orbits around the nucleus that are at fixed distances from the nucleus and have fixed levels of energy. And when energy is put into an atom, those electrons are going to be jumping around, basically, from one energy orbit to another and back down again, releasing their energy as fixed quantized wavelengths of light. Okay, so that is the Bohr model of an atom. And it's going to tell us about electrons, and we're going to see how electrons are going to then basically be responsible for the reactivity of different elements. So in the next lecture that we'll do in class, we're going to talk about the quantum mechanic model proposed by Schrödinger and see how it's related to this Bohr model, but it kind of takes it one step further.